In this video, we're going to look a little more closely at the Monte Carlo method for estimating pi. We're going to start with the pi estimate script that we developed in the previous video. And this time, instead of selecting values of x and y from 0 to 1, as we did previously, we're going to select values of x and y from -1 to 1. So this is a different range, but still a uniformly distributed random variable. And as you might imagine, to obtain values from -1 to 1, we simply multiply the random number from 0 to 1 by 2 and add it to -1. And this method, of course, works for any range from A to B. We go from A and then we do B minus A here. So everything else remains the same because we have points which are over 4 times as much area, but the fraction of points that lie within the circle compared to the square that lies around it is just the same as it was before. So if we were to run this script, we would get values very close to pi again, and again with that same statistical variation. But in order to illustrate how this method works, I'm going to do something else. I'm going to add another variable which I'm going to call r, and we'll see what that means in just a second. Oh, sorry, I can't call it r, I'm going to call it reg for rejected, and I'm going to call this t. I'm going to replace that, I'm going to call it accepted. Actually, I'll call that rejected underneath. So I'm going to keep a tally of how many points were accepted, in other words, were within r equals 1, and therefore contribute to the tally. So I'm going to take the variable accepted, and if r is less than 1, then accepted equals accepted plus 1. Else, rejected equals rejected plus 1. So as you can see, initially the value of accepted is equal to 0, but when I add 1 to it, I can now do something else. I can take the value of x and y that I have, and I can add it as a particular point. So I'm going to call it accepted x accepted is equal to x, and accepted y accepted. This might at first be a little confusing because accepted is the place in the array, so I'm accumulating the number of accepted points, and I'm accumulating their x values and their y values. And of course I can just copy those 2 lines of code, and I can do the same thing for the rejected points. So I simply copy rejected, 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 and I'm going to call this now the array Rx and Ry. These are 2 arrays of the x and y values of the rejected points. Well, why would I want to do this? Well, now I can plot what those values look like. So clearly, we hope that the accepted values will all be points within a circle, and the rejected points will be all the points which are outside the circle but inside the square. So we can visualize how this method is working. So I'm going to plot, and I'm going to plot the accepted x's versus the accepted y's. Now, of course, they have no particular relationship with each other, so I'm just going to plot them as red circles with no line joining them. So I'm just going to plot those to begin with so that we can see if it's working. So I'm going to run, and no value of t because the tally, of course, is now accepted. There we are, over there. So let's see if that works again. And we should see the points. So as you can see, I'm generating points over a square from -1 to 1, and the accepted points are only the ones which lie within r is equal to 1 within the circle. So if I hold on, okay, this is simple syntax. There are other ways of doing this, but let's turn the hold off afterwards. I'm going to plot the other points, the rejected points, in blue. Now obviously I can only do this for a relatively... I should have plotted the rejected points there. There we are. So doing this plot will only work for a limited number of points, say up to about 1,000 or a few thousand or so. So if I change the number of points I'm sampling, I just move this window across. You can see that a smaller number of points is a little less clear that there's a circle, but if I increase that number to say 5,000, you can see that it becomes much clearer. There we go. And of course, if I continue to increase that number, then eventually the plot will become rather ungainly. But anyway, the point of this plot is it shows how this Monte Carlo technique works. This is what's called an acceptance rejection technique, and it's named as such by its inventor, John von Neumann, who I believe invented it in the early 1940s. So the principle of the method that we were previously using is as follows. We select a point, and if that point is within some region, then I accept it and it contributes to the integral. So what we've done here is we've assigned values within this circular boundary as contributing to the integral, and if they lie within the boundary, they contribute with a probability of 1, which we haven't explicitly included here, but we can do if we wish. And the points which lie outside that boundary do not contribute at all. They contribute with a probability 0. Now that basic idea can be augmented by having a variable probability, which we can see a bit later on. But in its simplest incarnation, this rejection technique, this acceptance rejection technique, gives us a way of obtaining the value of pi. So this is what's known as the von Neumann rejection method.